Welcome, everyone, and welcome to the new semester of the IIT seminar series. And it is my great pleasure to be able to continue with this and to welcome Claus Rüffler, who's going to be talking to us today. So Claus is coming from Uppsala University, and the thing is, even those models of evolution where individual heterogeneity is taken into account very rarely incorporate ontogenetic changes, and I believe that is what we're going to be hearing about from Claus. So without further ado, floor is yours.
Yeah, thank you very much, Georgi, for the introduction, and thank you very much for the initiative to give me the opportunity to present my results here. I'm very happy to do so. So I'm going to talk about work that was led by my former postdoc, Marco Saltini, and to which my former PhD student, Paula Vasconcelos, contributed. And I kick this off with a picture with birds, since I'm a bird watcher. This is about a classical question in ecological research, and that is, under what conditions can competition for shared resources lead or not lead to the coexistence of similar species? And I just start with two empirical examples. So this is 4 species of the genus Sylvia that coexist in many places in the Mediterranean, amongst others here in Corsica, in Sardinia. And these authors, they did a very detailed field study looking at details of habitat usage and resource usage to come up with ideas what makes them coexist. A more modern version of this is a study from last year that asked how the large amount of grazers that we can see in African steppes can coexist. I mean, these are all grazers, one could think, eating the same grass. So this is a study from 2022 where they looked at a bunch of African national parks and now did meta-barcoding on fecal samples. And this shows a principal component analysis showing that all of these different grazer species apparently have non-overlapping resource usage. Of course, this question of coexistence in ecology has a long tradition in the theoretical arena too. And maybe the most recent review of this body of research is this book by Mark McKeepeek that appeared last year, where he takes this hierarchical approach, building up food web modules of increasing complexity, starting with a resource, then adding a consumer, adding a second consumer, or adding a second resource, and so forth, building modules of increasing complexity and asking under what conditions are these modules stable, meaning that all of these different players are able to coexist. He also takes it to a third trophic level. And what all of these models in McPeak's book have in common, and he acknowledged that, is that they are of the following type. Each node in these modules, representing a different species, is sort of described in the following way. So there's a number of individuals at that node that changes due to birth and death, where the birth rate is a function of all the population sizes of the other players in the food web and the environment. So said differently, the differential equations describing each node are of this form. So a single equation for each node, meaning all individuals belonging to a species are indistinguishable. So there's no structure within a node, within a species. And of course, we all know that this is very much not the case in nature, but it's of course a time-honored and valuable simplification. But most organisms in nature undergo some type of ontogenetic change, during which they also use different resources. So in holometabolic insects, the larvae are completely decoupled in their niche from the adults. And the same is true, for example, in amphibians for tadpoles and the adult frogs. And I'm, of course, not the first to think about this. And one person here in the audience made a career about thinking about these things. But I just want to highlight a little bit more the importance of this. So in this review by Earl Werner, that's now time-honored, he states, I have estimated that perhaps 80% of animal species undergo a metamorphosis during the life cycle. Additionally, a large proportion of direct developing species exhibit marked shifts in niche during ontogeny and therefore effectively have complex life histories. So saying that almost all animals undergo some form of ontogenetic niche shift. And I would argue that this perspective, although it is acknowledged in the theoretical literature, it's not yet the backbone of the theory in community ecology. And maybe with this work, we can contribute a little bit to that. So what we are going to do is to compare two different types of models. One which is simple life cycle here on the left, and one with what we call a complex life cycle, where individuals undergo ontogenetic niche shift. And we are interested in how competition for shared resources can contribute to the emergence of diversity in this consumer species that either have a simple or a complex life cycle. The models are pretty much standard, but for the fact maybe that sort of this model where we add the ontogenetic niche shift, but the ingredients are pretty much standard. So in the simple life cycle model, we have here individuals N that reproduce through birth, and this birth rate is a function of the usage of a continuous spectrum of resources, where resources are characterized by a one-dimensional value Z, and we assume that resources have a Gaussian distribution in the absence of consumption. And how well these consumers can feed on this, that determines their birth, and then we will add evolution to that. For the structured model, we assume that juveniles feed on a different set of in different resource distribution, and that their efficiency with which they feed on that resource distribution affects their maturation rate. And once they are adults, they feed on a different set of resources, on an adult set of resources, and how well they are doing at that affect the birth rate. And now let me go through some equations. So this is very much time-honored standard. So we take the approach that we derive a competition model from a predator-prey model following Robert McArthur's idea. So for the resources, we assume that resources grow according to logistic growth in the absence of consumption for each different trait value Z, where Z affects this carrying capacity, so the abundance of the resource and the absence of consumption. Then there are consumers N and possibly many different species, indexed I, that feed with a feeding efficiency on that resource with a linear functional response, where the feeding efficiency depends on the particular trait value of that resource and the trait value of that consumer species. And I will talk about this later. Then the consumers, they give birth according to their total resource consumption, so integrated over all types of resources Z, where all resources have the same conversion coefficient C, and consumers die at a constant rate D. So going a bit through the ingredients of this model, this carrying capacity function, we assume, as said, it's a Gaussian function of the trait value Z, with the standard deviation that we call omega. And this feeding efficiency of the consumer, that's also described as a Gaussian function with a standard deviation sigma, that describes the match of the consumer trait and the resource trait. So if the consumer trait is equal to the resource trait, then we are here at the peak of this Gaussian function. So that's the part of the resource spectrum at which the consumer is best. And with increasing mismatch between the Z value of the resource and the X value of the consumer, the feeding efficiency decreases. And if we assume that the resource dynamics are faster than the consumer dynamics, we get a quasi-equilibrium, a quasi-resource distribution, which shows the shape that the consumer feeds a hole into the resource distribution. If we assume Gaussian functions for everything, we are able to obtain an explicit expression for this quasi-equilibrium. We can plug it in here, and then we get a single equation for the consumer dynamics, where the birth rate is now given by the right-hand side of this. So there's a birth rate in the absence of competition, and this term that accounts for competition, where this B0 and this alpha, they are quite lengthy and complicated equations, but they can be obtained by solving this integral. This is the case for the unstructured model. And now we assume that this consumer trait value X, that's an evolvable trait. And we look at two different approaches. Either this evolves by small mutational steps along the line of adaptive dynamics. So then we look at adaptive radiations and ask what is the species richness at the end of adaptive radiations. And the second approach is that we look at an immigration scenario. We randomly choose phenotype, we add them to the community, we see whether they can establish, and we repeat this process until the community is saturated. For the gradual diversification scenario, we obtain graphs like this, and I'm sure that all of you have seen graphs like this. So the trait value on the x-axis, time on the y-axis. For this model, everything is symmetric. 0 would actually be a branching point for the consumer trait value. But since in these stochastic simulations, the mutational step size is not infinitely small, it diverges a bit earlier, and then, continues to diverge. And then we can count the number of tips here at the end of the radiation when no further splitting occurs. Same procedure for the model with complex life cycle. So now there is a juvenile trait value xj and an adult trait value xa. And since we are mostly inspired by holometabolic insects, we assume that these two trait values, they are independent of each other. So morphology of larvae and adults and insects, they are pretty much decoupled. So these can evolve independently. And doing the same process, plugging in the quasi-equilibrium of the resource dynamics into this equation, we derive at this Lotka-Volterra-ish type of competition model, but now where the competitor is population structure. The juvenile class increases due to birth and decreases due to maturation, individuals leaving the juvenile class to maturation, and individuals leave the juvenile class to death. The individuals enter the adult class due to juveniles maturing, and individuals leave the adult class due to death. And as said, we have these trait values. Adult trait values affect the birth rate, and juvenile trait values affect the maturation rate. This is pretty much the description of the model, and now I will jump to the results. And in these results, we will vary. Oh, okay, sorry. This is sort of then how an adaptive radiation looks for the structured case. So we have the juvenile trait value on the x-axis, the adult trait value on the y-axis, and time on the third axis. So this is now an adaptive radiation in a two-dimensional space. And now in these results, we will vary the width of this feeding function, because we know from earlier theory that this is what affects the diversity that emerges in such radiation. So smaller feeding functions means a given resource distribution has, heuristically speaking, more niches, so more species fit in there and can coexist. Okay, the first slide from the results. So what this graphs show is the endpoint of adaptive radiation. So the above panel is for the complex life cycle, the lower panel for the simple life cycle. So we have here the juvenile trait value, the adult trait value, and for the simple life cycle, there is just one trait value. So these dots, the way you have to think about it, they are the tips of at the end of the radiation in trait space. So what do we see?
Klaus,
yes,
Klaus, can I ask you a question?
Absolutely.
About the previous slide where you showed it. No, where you showed the dynamics actually of this So is this unique? Or are there alternative outcomes possible? Because this is a stochastic simulation, and I'm just wondering whether the endpoints are unique in this case, which they probably are in the one-dimensional case, but in the two-dimensional case, I don't know whether that's the case.
Yeah, excellent question. No, they are not unique, and I can show you later a graph showing 10 repeats of the same simulation. Yeah, so I will come back to that.
Okay.
But the stochasticity actually matters for the final community composition. Mm-hmm.
Yeah.
So
I have a question very quickly.
Yes.
Is this sigma A or sigma J?
So in this panel, okay, yeah. So in this panel is where we keep the sigmas for the juveniles and adults the same, and the next panel we vary the sigmas for the juveniles and adults. So this panel is more about the comparison between complex and simple life cycles to make that comparison sort of easy to grasp. At the moment, we keep this niche width, the width of the feeding kernel for the adult and the adult life stage the same. And the next slide, we will allow for different niche widths.
Thanks.
So the wider the niche width, so the wider these Gaussians, we get fewer species in the radiation. So if we look at the simple life cycle, 3, 4, 6, yeah, more and more. That makes total sense. We know that for a long time. We see the same for the complex life cycle. And now when we saw these results for the very first time, we were quite surprised, because in the case of complex life cycle, there's large area of the trait space that's not occupied. So these communities, they tend to be organized in a diagonal way or in an anti-diagonal way with considerable noise, but it's not filling the two-dimensional trait space evenly. And this is sort of one of the main things that I will delve upon, and in a way, maybe one of the main results of this research, and I will try to make sense of this in the rest of the talk. But just for the moment, note, right? So this species here has a negative trait value for the juvenile trait and a negative trait value for the adult trait, and the two traits are positively correlated. You could, in principle, imagine that should be this guy, right? Sort of that has juvenile and adult trait values from these two species in a combined way. But that's not what we see in gradual radiations. Okay, so now this is a complicated slide. So I will walk you through the results slowly. So now we actually allow for the adult and juvenile niche width to vary. So on the x-axis, we vary the adult niche width, and the color symbols are different juvenile niche widths. So we look at this dot here, that is adult niche width is 0.15, juvenile niche width is 0.15. We look at the green triangle here, that's adult niche width 0.3, juvenile niche width 0.3. The blue square here, 45 for both, and so forth. And these symbols are the results from simulations where the juvenile niche width is wider, is broader than the adult niche width. While if we look at this case, so these two symbols are cases where the juvenile niche width is more narrow than the adult niche width, and here it's the opposite. And this is now the number of species at the end of a radiation based on 10 simulation runs per combination of niche widths. So what do we see? Oh, and I should add that the black horizontal bar is the species richness in radiations of simple life cycles, where simple life cycles, they have the same niche width as these adult niche widths. So meaning, so for example here, this is in the complex life cycle case, both niche widths are 0.3, and also the in the case of the simple life cycles, the niche width is 0.3, and then we see it's the same number of species in the radiation with complex life cycle and in the radiation with simple life cycles, given that all niche widths are the same. But if we look here, actually in the simple life cycle, there are more species, like on average, one more species. I mean, this is over 10 simulation runs. And if the juvenile niche width is broader than the adult niche width, then the simulations with complex life cycles actually result in lower diversity. And more generally, so if we look at this case, so if all niche widths are the same, simple and complex life cycle give similar results. If in the model with complex life cycle, the juvenile niche width is more narrow, we get a higher diversity with complex life cycles. But if the juvenile niche width is broader, we get a lower diversity with complex life cycles. Maybe kind of intuitive. But the basic take-home message from this is that complex life cycles do not inherently lead to higher diversity, right? If these niche widths are the same, complex life cycles and simple life cycles give very similar diversity, which is essentially due to this fact that with complex life cycles, the communities do not fill the two-dimensional space, but they arrange along a one-dimensional manifold within this two-dimensional space. So in a way, we place this line here diagonally. And that's sort of why we don't find inherently more species. Okay, I will come now to the immigration scenario, and then I'll try to make sense of this. So in the immigration scenario, what we do is we randomly select phenotypes, we add them to the community, we run the population dynamics until there's no further change. So species might either establish or not. If it established, it could potentially drive other species to extinction. And we do this, we iterate this until, I think, what was it, 100 additional immigrants could not establish. So then we consider the community saturated. So there are two things to notice. First, maybe the less uninteresting one. The less interesting one, we get clusters. So here, these dots are clearly isolated. So there's character displacement acting. Here we get clusters. Well, this in a way is an artifact of how we do the simulations. In the gradual evolution, we use stochastic adaptive dynamics simulations. So that is, we assume if a mutant is able to invade and if the resident is not able to invade back, the mutant replaces. So we have a trait substitution sequence. While in the immigration case, there is no ancestor, right? I mean, this is just any random. So we don't remove any species if a new one invades. And this results to these clusters. And essentially what's happening, and that's also a known phenomenon, the population dynamics, they just become infinitely slow. So eventually one would expect that this is thinning down, but it's computational not feasible to do that. So that's why we get clusters. So that's not so interesting. The more interesting thing is that now we get the complete filling of the niche space. So we get a rectangular community. So summary here, the above case is the slides that you've seen, the results for gradual evolution. The lower case is now the results for the immigration case. Again, simple life cycles, complex life cycles. With simple life cycles, there's essentially no difference other than that we get this clusters. So here we have one clearly isolated dots, which becomes two dots here, and this becomes sort of increasingly messy. With complex life cycles, yeah, we get rectangular communities. So not just these two species on a diagonal, but then these opposite combinations of traits are always also realized. And that...
Klaus.
Yes.
Klaus, you said the population dynamics become infinitely slow.
Yes.
But so there is some kind, are there differences in abundance between these dots? Because you only show the trait values, and
yes,
some of them might be something like what, 10 to the minus 9 in density or so, or
yes.
what are they different?
We do have a cutoff, but it's a pretty conservative cutoff. And there are definitely differences in density. So it's most likely, we didn't dig into this in detail, but it's most likely that one of these dots is sort of has the highest abundance and the others have much lower abundance. I agree with the intuition, but we didn't. But then there was a cutoff, and then we removed the species because it's ODEs, right? So they never reach zero deterministically. Sure. So there is a cutoff, and then we remove the species.
Yeah.
Okay, so now let's try to make sense of, so what this says is actually that under the immigration scenario, complex life cycles leads to much higher species diversity than under the gradual evolution scenario. So here we have much higher, we did plots where we compare species diversity. So this is kind of to the power 2, the number of clusters compared to the case of simple life cycles. So what's going on? How can we understand this contrast between gradual evolution and immigration? So these species, they compete with each other, and they compete at 2 life stages with each other. So they once they branch, they experience character displacement, and they experience this character displacement simultaneously at the adult life stage and the juvenile life stage. So 2 species that differ in both the adult life stage and the juvenile life stage compete less strongly with each other than species that differ at only one of their life stages. So that's a key thing that one has to keep in mind. So character displacement, in a way, tries to maximize this diagonal distance. That would decrease competition at both life stages. So now we look a little bit in more detail at how this diversity emerges. So what this series of plot shows is it's a time series plot of the build-up of diversity for this simplest case where we get either 2 species or 4 clusters. So, and what these contour lines show, it's actually not invasion fitness, what one might think, it's establishment probability, because that is what we use in the computational algorithm. And it's sign equivalent to invasion fitness. So the dots are location of resident trait values, and the contour line that goes through these dots, that's the 0 contour line. So these guys have a negative establishment probability, while these guys have increasingly higher establishment probabilities. So we see, so for the parameter values that we choose here, the juvenile density of the consumer is higher than the adult density. So competition is stronger among juveniles than among adults, and that makes that there's a branching point in the juvenile, in the direction of the juvenile trait. So if this is a resident, yeah, it goes up on both sides, but in the adult trait value, it's actually stabilizing selection. So we would get branching first in the juvenile trait value. So let's assume they branch and they happily diverge, driven by character displacement. During this process, the population size actually increases because, yeah, of character displacements, they use different parts of the niche spectrum. So the summed population size increases, which causes that at some point, the adult trait values become also branching points. So we see at this point, if I look now vertically, the arrows go into this colored region, which has a positive establishment probability. And this would happen here on both sides. But actually, this selection in this direction is still much stronger, but now these two species sit at branching points also and for the adult trait. And now what we see is not that these things branch simultaneously, but that a symmetry breaking is taking place and that we end up with two species that are arranged diagonally. How does a symmetry breaking happen? So let's look at this in a bit more detail. So let's assume that we are at this point and one species branches, say this species. So now these two species can coexist. And now if, say, this species is mutating and is decreasing its juvenile trait value, then what happens is not only that its ancestor is going extinct, but also this ancestor, this type is also going extinct. It is squeezed out by this type that is now more specialized in both the adult trait value and in the juvenile trait value. And that's symmetry is broken. We get this diagonal community. And from then, things continue in this way. These two things now diverge diagonally. They cannot occupy this, the evolutionary path in this direction is cut off by a fitness valley. Same here. As they diverge, these become isolated islands. And then, so this is now, it's not exactly symmetric in this process. Therefore, this fitness peak, which is sort of here, is left. So there's an island, but it cannot be reached through gradual evolution, but we can put an immigrant species there and it can establish. Once we do that, this fitness peak pops up. It's not reachable through gradual evolution, but we can place an immigrant there. And we end up with a community of 4 species that now evolve gradually to these 4 fitness peaks. There's a different way. I have a second scenario here how this symmetry breaking can take place. So let's say we have branching here. And now if these 2 species are diverging asymmetrically, which in a stochastic simulation always happens, this species will not be at a branching point anymore, but it will experience directional selection. In this case, it's very subtle to see here, but now this guy can only, in the adult trait value, only evolve upwards. If it does so, eventually this species is squeezed out because this species is experienced full competition with this species in the juvenile trait value and full competition with this species and the adult trait value. So symmetry is broken. We end up with this diagonal community and we are trapped in this. And yeah, as said, the path So this other areas is cut off, but it's not cut off for immigrants that take random phenotypes. Yeah, I hope that explains these results. These results of the studies are published in a paper a couple of months ago in the Ecology Letter. There's an accompanying manuscript. It's just a preprint on bioRxiv. I could talk about this, but I think the time is pretty advanced, so maybe I better stop and open the floor to discussion. But Jörg, you'd tell me.
I think it's really up to you.
Oh, okay.
So if you have a strong preference, let us know.
I mean, I think this is not very, it doesn't take very long. I keep that very brief.
I think you should.
So what we do in this manuscript, which is part of Paula's PhD thesis, and this is actually, this one is what we did first, and later we added this one. We actually just have 2 resources per life stage. So this is really, I come back to my own PhD research. So there's 2 resources per life stage, 2 juvenile resources, 2 adult resources. Otherwise, the model is exactly the same. So that now means we don't have this Gaussian feeding kernels. We have a trade-off. So this is the feeding efficiency for resource 1. This is the feeding efficiency for resource 2. And we assume there's a trade-off. So evolution happens along one of these lines. And we allow for different curvatures of this trade-off. So there can be weak trade-offs where the generalist has a pretty high feeding efficiency for both resources. There can be strong trade-offs where the feeding efficiency of the generalist is pretty low. And what we did is sort of in this model, we actually first played with parameters that affect the population composition. So is the population juvenile dominated? Is it adult dominated? And how does it affect branching in either the juvenile trait or the adult trait? And the simple answer is the stage that has a higher density, it experiences stronger competition, and that's what drives branching. So in juvenile dominated population, branching happens more easily in the juvenile trait, and adult dominated population branching happens more easily in the adult trait. And then we look at the coevolution of these 2 traits. So this is then again consumer populations. So where now on the x-axis is actually it's the phenotype of the juvenile, which is now the position along this trade-off curve. So if you have an intermediate trait value or generalist, so the triangles is the trait value of 0, the circle is the trait value of 0.5, the square is the trait value of 1. So as sigma changes from 0 to 1, we walk along this trade-off curve. So, and this is now what is plotted here on the x-axis and on the y-axis. So this is where the species is a generalist for both the juvenile and the adult resources, and that's a branching point. And that then we observe pretty generally, again, we get this diagonal community. So we get a community that sits here or here, and not 4 species. But what we could do in this model is we could break the symmetry. So in the other model, we could get the math only working by assuming everything is Gaussian, so everything is symmetric. But in this model with 2 resources, it was easy to assume that the 2 resources in the life stages differ in their growth rate or carrying capacity. And if we do that, we could actually get trimorphism under gradual evolution. So now the branching point is not here in the center, it's shifted. So first branch is here, but then it branches again, and we can actually get a trimorphic population, but never a quadrimorphism through gradual evolution. So now I have a master student where we take a different approach to this complex life cycle model by Marco, that gives us a much larger flexibility in the resource distribution, so that we can actually investigate any resource distribution, that we are not tied to this Gaussian resource distributions anymore. And then I'm curious to see how these results actually hold up. Yes, and maybe I just quickly come immediately to Andre's question. So this is 10 simulation runs for a particular juvenile adult niche width, and this is sort of how these look as a result of stochasticity. So there's always this diagonal structure. Sometimes it's more clear, sometimes more fuzzy, but the interesting case is, even in this more fuzzy case, we run it, it doesn't really change anymore. I stop here.
Thank you so much, Klaus. So if anybody has questions, please raise your hand in the chat and I shall call on you. So are there any questions? Yes, Rafa, please go ahead.
Thanks, Yuri. So Klaus, thanks for the talk. Very interesting. So I have a number of questions. I guess let's start with, so you spent a lot of time explaining the difference between the rectangular shape when we have integration and a diagonal shape when we have gradual evolution. Would another way to put this be that you have a fitness landscape that is rectangular in shape, and when you have immigration, you're allowed to visit the entire fitness landscape. But when you have evolution, you can't, as you mentioned at some point. You can only travel in small increments and where you currently are, and therefore you're going to walk in the direction of maximum fitness, which in this case is to maximize the distance, which is on a diagonal. Whereas if you're allowed to introduce anybody at any point on the plane, then you can visit the entire landscape and its local maxima, which would be rectangular, because that maximizes distances on a plane. Would that be an accurate way of thinking about this difference in shape?
Yeah, I'm not sure. So at least I wouldn't phrase it this way. So what this figure shows, of course, the fitness landscape is dynamic. So there is no rectangular fitness landscape. I mean, there's a rectangular trade space, but the fitness landscape, sort of illustrated by these contour lines, completely depends on who are the resident species. So it is that under gradual evolution, the fitness landscape changes in a way that some potential endpoints are cut off to the path of gradual evolution. And I'm not sure that is the same as you are saying with other words.
Okay. All right, I'll think a little bit more about that. So my other question was, when you mentioned the clusters, you dismissed them as uninteresting. But if we were to think about what you actually would expect to see, right? Let's say nature actually follows your model, right?
Yes.
You said one thing that would happen is it would take forever for one species to exclude the other.
Yes.
Well, therefore, if I look at a world where time isn't not infinite, I would actually expect to see the clusters, no?
Totally, yes. I mean, totally valid. And of course, if I would make the adaptive dynamic simulations properly individual based, I should see the clusters, definitely. Then every dot should be a cloud, and this is what nature is. So I agree. I guess what I meant that it is not interesting, it's not an interesting difference between the two cases, because there it's based on different algorithms. And I fully agree with you that this is the thing that we see in nature, and the better simulation algorithm would be one, or the more realistic algorithm, I should say, is one where we also would see these clusters under gradual evolution. And of course, right under gradual evolution, these clusters, they would be under mutation selection balance. So it wouldn't take forever until they disappear, because it's always replenished through mutation. So yes.
Okay, I just have one last question. So in the model, you didn't at any point impose that adults of one species should compete with adults of another, and juveniles should compete with juveniles. In principle, juveniles of one species are allowed to compete with adults of another, and vice versa, correct?
not sure. Sorry. All juvenile individuals from all species together compete, and all adult species from all adult individuals from all adult species together compete with each other.
Right. And but it's also possible for adults of species A to compete with juveniles of species B.
No, that's not what we addressed, right? So we are in this world, like insects, metamorphosis, really a proper ontogenetic niche shift. Adults occupy a different world, so to say, than juveniles. Of course, that's not true for all species. And I mean, what you suggest, I guess that's sort of Andre's world, where we look at fish species. They grow, they undergo ontogenetic niche shift through growth, but larger species can usually still forage on the juvenile resource. And then you get a different scenario. But that's not something that we consider.
Okay, thank you.
Thanks a lot. Colin, please, or Colin, I don't know if you still want to say something.
I was curious about mechanisms that might cause sort of a spreading of trait usage between adults and juveniles, but those are all kind of predicated on those sharing overall resources. So I think if juveniles and adults are in two completely different worlds, there's no reason to have mechanisms that would encourage, whether it's a portfolio effect or spatial aggregation that might cause competition within a species. So I don't think my question makes sense.
Okay.
Thanks anyway. And then Geza, please, you're next.
If I understand correctly, the two traits, juvenile and the adult traits, are evolving completely independently.
That's right.
Okay. Of course, this is consistent with your previous answer that these are two different niche space. But I think in many situations they are not really independent.
Exactly. Again.
Yeah, but then of course, no, I understand that it would be a completely different problem. So then, what was that surprised me that we see this kind of positively linear correlation between the two traits, or a negatively linear correlation of traits. So, of course, if there were a physiological correlation between them, we could not have both of them. But then, what is the origin of this band-like arrangement of? I guess it is evolutionary, and not.
So you mean whether it's positively correlated or negatively correlated?
And that they are correlated at all.
Aha. Okay.
I don't see the ecological reason for it. Probably okay. It is the food comes from the branching pattern.
Well, I guess, then I failed to some extent with my presentation. So first of all, let me come back to the first part of what you said.
Yeah, okay.
So these can be positively correlated or negatively correlated, and that in our model is actually completely stochastically. So that fully depends on sort of this symmetry breaking, and that's stochastic, whether it results in this community or in the reverse community. So if we look at many simulations, we find equally often positive correlation or negative correlation. And that's sort of due to the stochasticity. And then if we would have a species where, due to underlying genetic correlation, so going back to fishes, where of course the phenotype of juvenile fishes and large fishes, they are not at all completely decoupled, right? So I'm not an expert, but I expect they are strongly positively correlated. So that would then, if we would add something like that, then that would of course give a bias towards this niche, this symmetry breaking, and it should always happen in one direction. Okay, but now I guess sort of your real question was, why does this symmetry breaking happen And why does that then lead to these diagonal communities, be they positively correlated or negatively correlated? That's sort of your second question, or your real question.
Yes, of course. Whether in this context, whether it is positive or negative is just a random symmetry breaking. This is not clear for me. But then, why it is not just fully independent evolution of the two traits?
So the two traits, they mutate fully independently, and they mutate in all directions with the same probability. So that we see these emerging diagonal communities is a result of this fitness landscape and sort of, establishment probability for certain phenotypes, allowing them to invade or not. And let's see. I mean, I thought I tried to address your question when I talked about the transition from this panel to this panel. So let's say once we are in this panel, Gesa, do you agree that the path to a rectangular community is cut off?
Klaus, I'm not sure if we're watching the same thing. Something.
Oh, sorry, I stopped sharing.
No, you had the full screen mode on, but you looked at your.
Yeah. Sorry. Okay. So, okay, sorry. I'm here. So, Gesa, so are we on the same page that once we have this community, the path to a rectangular community is cut off?
Yeah.
Okay, so then I guess your question boils down is, how do we get from this community to this community? Because at this time, sort of, we could still get a rectangular community, a complete niche filling, right?
Yes.
So what happens from here to here? And I sort of, on this slide, describes two scenarios explaining the symmetry breaking. And the symmetry breaking, it wouldn't happen if we would deterministically implementing the canonical equation of adaptive dynamics, where branching would always happen simultaneously, right? So if this would be described, I have two canonical equations. Now these things sit at the branching point in the adult traits. I simultaneously add two, like a new type here and a new type here in a symmetric fashion. I let the canonical equation run, everything is symmetric, then I would get a rectangular community. But that's, of course, a very, very contrived. I mean, it's an extreme case. And what we do in these simulations, I mean, they're not individual based, but they are stochastic.
Yes.
What we do is that the next mutant that we add to the population, it is drawn randomly, weighted with the population size of the parents so that mutations are produced, and the establishment probability of all the different possible mutants. So we compute all the possible mutants. So that's something that I skipped. I mutate, for simplicity, mutation step size is fixed. So that it's not drawn from a normal distribution. So we really, in this case, there are 8 possible mutants in species 1, up, down, right, left, in species 2, up, down, right, left. Which is the next species that we add? It is the one, so we draw that randomly, weighted with what is the abundance of the parental types. So that's about the production of new mutants. And what is the establishment probability of each mutation? Sort of that they escape the stochastic boundary layer, so that they escape demographic stochasticity. And then we draw randomly that mutant and we add it. And then we ask, is it replacing the parental type? If yes, we remove the parental type. If no, then then we are actually at a branching point. So the simulations are significantly different from the canonical equation. And this is what allows for the symmetry breaking that is described in two scenarios. The top row of panels is one scenario, and the lower is the second scenario. What's happening in both of these scenarios is, due to stochasticity, we get a symmetry, and sort of we get kind of types that are diagonal, and these types so we get a triangular community, and in that triangular community, this species that is at the 90-degree angle, that is squeezed out by competition from these two species, because it competes at full strength at both the juvenile and the adult stage. It's just that it does so with different species. So this species, or I should say actually, in this case, this species competes very strongly with this species in the juvenile trait. So they are very similar here, but this guy is actually more specialized. So this one sort of is really outcompeting the juveniles of this species, is really outcompeting the juveniles of this species, while the adults of this species compete at full strength with the adult of this species, because they have the same trait value. And in combination,
it plays a role that also the adults and the juveniles all compete with each other in the same niche space, and that creates this interaction, this kind of deformation of these contours, right?
Sorry, so adults and juveniles, they do not compete in the same niche space.
They're not in the same niche space. I thought they all compete on the same one-dimensional resource axis.
No. Okay, sorry, very important. So this resource axis describes, say, we take tadpoles. This is something, this is, so we take frogs. This is tadpoles. This is algae in the pond.
Yes.
This is frogs. This is like insects on land.
Okay.
So this is the ontogenetic niche shift, right?
Right. All right.
They are separated resource axes.
Oh.
So there's no direct interaction between any juvenile or any adult individual. Sorry if that was not sufficiently clear.
Okay.
Anyway, I don't know, Klaus, if you wanted to continue with that, or
with Geza's question, or I guess sort of maybe I hand over back to Geza. Is sort of all the things that I talked, did it clarify something in your mind?
Okay, thank you. So maybe I understand.
Maybe we should go on for the sake of time. So Axel, you're next.
Yeah, I try to make it not too long. So I was surprised about the result. You say, okay, if we have random invasions, you get something very different from if you have evolution. But would this phenomenon also arise if you had a two-dimensional niche spaces? Because on one dimension, it's always difficult to get past the guy next to you or the girl next to you, but in 2 dimensions, it's easy. So would this persist?
Okay, let me see whether I understand your question. So is it, you're saying, what if the juveniles would be described by 2 juvenile trait values,
yes,
and adults would be described by 2 adult trait values in combination a 4-dimensional trait space?
Wouldn't they then not all spread over both 2-dimensional niche spaces as a result? Because then it's easier to move around.
Okay, so we have a 4-dimensional trait space. So then I guess I would have to think hard what that now means. What's the diagonal community?
Okay, maybe it's too difficult a question.
Sorry, say it again, Axel.
Yeah, maybe it's too difficult. Maybe.
Yeah, I mean, yeah. To be completely honest, I haven't thought about it, and on the spot, I'm not sure I have an intuition about this.
Okay. Then something about, since people got excited about the clusters again, if you did, I thought you can't get, if the clusters are an artifact, as you say, then it shouldn't be possible to get the clusters if you invade the species at an abundance that equals the cutoff abundance, because or am I wrong?
Aha. Okay. And that's, I have to admit, that's a technical detail that I don't have in my head. So the question is, do we add immigrants at a density above the cutoff? And I guess we have to, but I have to go to the paper to look that up in the appendix where we describe the algorithm. Good question.
Okay. And then there's a very small final part. The people, it's known that these Gaussian, if you make everything Gaussian, you can generate artifacts. And in some kind of cases, you can make infinitely many species coexist.
Yes.
Isn't this a problem?
So, I mean, luckily we have Gesa on board, who is an expert on this. So my take is that, so since this is sort of a Lotka-Volterra competition model where B and alpha, they are not Gaussian functions, right? So if we take the Lotka-Volterra competition model straight on, as Döbli and Dickmann analyzed it a dozen times, then this competition kernel is a Gaussian function. And the carrying capacity is a Gaussian function. But here we take a step from the resource dynamics, sort of we derive the competition model from an underlying predator-prey model. And in that process, there are no Gaussians anymore in the competition model. So
okay.
These functions are pretty complicated. I have them somewhere down here. This is how this M0 and B0 looks, and this is how these alpha look. So I think we are safe from this degeneracy that Gesa and also Georgi investigated. But correct me if I'm wrong, if I'm too optimistic.
Okay, thank you very much. Thank you. That's good to hear.
Thanks. It's a bit difficult to say because, especially because this slide, the other slides were nicely Gaussian. These ones are some quadratic form, and one would have. But actually, okay, it's very easy to check. Just add a little constant to the m's.
Okay. But then, I mean, I guess sort of the results at least suggest that nothing weird happens because we do get discrete clusters, right? So this issue with Gaussian functions was about a continuous niche filling and not the community falling apart into discrete clusters, and we do see discrete clusters. So I feel I'm safe, but
yes, agreed. And sorry, I don't want to linger on that point because of the people, but I fully agree. So Atma, please go ahead.
Hi, thanks, Klaus. My question is, so in the gradual evolution case, there is no space filling, and it sort of makes me ask if we can completely forget about all this ontogenic niche shift and just keep doing what we have been doing with not considering complex life cycles and just say that there is going to be character displacement. And in the immigration case, we just, this is actually interesting to me because is it full space filling or is there character displacement?
Oh, there is, of course. I mean, it does not, you see, in this case, it looks like complete, but that is because the dots are so close. And then if each of them is a cloud, if it looks like continuous, but I believe it is not. So if we would look at what André suggests, really look at the abundance of these dots, that there is still sort of discreteness. And it's, we see it more clearly here. So I don't think it's actually complete niche filling. So we still have, so to say, this old wisdom of limiting similarity. I think it still applies, but it's
so if limiting similarity applies in both gradual evolution and immigration, then why not just go back to the old way of thinking in the gradual evolution, forget about complex life cycles? I'll just assume that there is no ontogenic niche shift. And in the immigration situation, I'll assume that there are two resources, and now there is just going to be limiting similarity in two axes, instead of thinking about the details of there being an adult and juvenile life stage.
I mean, now I am critical towards my own research. I think we still have to see whether this is robust if one plays with the model, right? I have shown you if there are just two resources and I introduce asymmetry in the resource distribution, I get not a diagonal community. I still don't get a rectangular, but I can get a triangular. And then, of course, we also have to keep in mind, I mean, okay, it's adaptive dynamics, pretty small mutational step sizes, and that's maybe very often a good approximation. But sometimes a large effect mutation might come along, like appearing like almost like an immigrant. So if we really want to understand nature, I think it's too dangerous to fall back on like adaptive dynamics simulations and say that's what it is.
Thank you.
Thanks so much. And Jonas, please go ahead.
All right, thanks. Claus, could you go back to slide 26? So yes, I was wondering about the diagonality, and of course, I instead have questions about the rectangularity, just to sort of complete everything. So what I'm wondering is, if we look at panel D here, and we imagine that the two residents here have been evolved, say, deterministically by the canonical equation to exactly occupy their fitness peaks.
Yes.
That would emerge. Would the off-diagonal two invaders have exactly 0 invasion fitness?
They would.
Okay, that helps me understand the rectangular case. So there is, in some sense, some kind of neutrality going on.
Exactly. So as a matter of fact, so if we look at this rectangular community, we don't have mutual invasibility of all 4 species.
Right.
So if they are completely symmetric, they are sort of, it's not a protected polymorphism.
Right.
And of course, I mean, in the simulations, it doesn't break down, but that's, I guess, because there are small asymmetries in the simulations. But in a completely symmetric world, we get neutrality.
Okay, perfect.
Yes.
Thank you.
And maybe now that starts a whole cascade of new questions.
Are there any cascades of questions or otherwise? I might have a very quick one, hopefully. In that graph you showed with the correlation, anti-correlation, it almost looks like you can get these mini Simpsons paradoxes that not even that one, the one that you showed at the end with the replicated simulations, I think that one will illustrate it better. If you go down, it's one of the slides, right? It's similar to what you were showing with the diagonal dots, but it was the one that you were showing to Andre.
Oh, sorry, the 10 repeated runs.
Exactly. There we go. So look, if we look at the top left one, it's like a Simpsons paradox kind of thing, that yes, there's a negative correlation, but there are 2 clusters, one where the juvenile trait is negative and one where the juvenile trait is positive. Within those clusters, it's a positive correlation. Does that have any deeper meaning, or is this an accident?
I mean, well, we have the same here, actually, right? We have the same here. We have the same here. So I guess, I mean, whether it's a deeper meaning, I think it's all a result of the stochastic community assembly that once you're on a certain track, it cuts off other pathways. And right, so it could be that these guys sort of live in they are more strongly interacting with each other than these. So they make their own diagonal community, and these make their own diagonal community, and they happen to be in two different directions. So, I mean, I think it's hard to explain this in detail, since this is a result of, I mean, really each simulation looks different. But yes, it is interesting to note that, I mean, they're not strictly like always on a line.
Klaus, isn't this a result of simply what happened in the one-dimensional case as well? You have a spreading of the types to actually minimize competition. And now you have that same spreading, but then along two axes, and you can, so the graph, the panel that Georgi referred to the top left, if you just look in the vertical direction, the dots have been spread out as much as possible, and in the horizontal direction as well. So it's just the adults minimize the interspecific competition among themselves, and the juveniles minimize the interspecific competition among themselves. There is some coupling between the juveniles and the adults, and that might mess things up. But when I look at your graphs, I just think like, okay, it's the adults that somehow try to move away from each other as much as possible, and the juveniles fill the space.
Yeah. And I guess, I mean, this is sort of becomes maybe a bit clear if we look, oops, yeah, here, right? So if we look, these two dots are exactly where you also have two clusters.
Right.
And these four dots, I mean, they're in the same position as four of these clusters.
Yeah.
And actually all of these dots, they are at the position where we then also get the cluster. So yes, so there is sort of a, and there are different ways of permutations of filling this.
Yeah.
I guess I have to think a little bit more about it, but I guess it makes sense.
And about your maturation and birth rate, how, because a lot of results that were even if you go back to the paper by Schreiber and Rudolph on where they used the juvenile adult, so there is bistability, and there is a lot of results depend actually on the symmetry between juveniles and adults. If there is, if they are symmetric, if this food supply and the per capita rates are all the same, that influences your dynamics a lot. So are these B's and M's, how different are they? And do you, for example, have the same carrying capacity function for the adult and the juvenile resource?
Okay, let me answer the second question, because for that I have a slide. That was a question.
I saw the equation.
Right, so this is where this is all the results that I presented so far, where the carrying, sort of this maximum carrying capacity for juveniles and adults is the same. So the baseline scenario was based on this. And now we break that symmetry, making either the juvenile carrying capacity increase that and decrease this, or the other way. And that has an effect actually on like, you see here, the angle of this community, right? So, right. But the qualitative pattern is independent of this. I mean, at least for these cases that we looked at. Okay, that maybe answers that question. But then you asked, how different are the M's and the B's? So, I mean, first, it's interesting that you mentioned this paper by Schreiber, because that's actually how I started to think about all of this, that I read that paper. Thought, oh, but now we should add evolution to this.
Yeah.
But then Sebastian's paper is all about population dynamics and complicated population dynamics, and he's excited about that model. So for those who haven't read that paper, they look at this model, but whereas there's just a single juvenile resource and a single adult resource. Otherwise, it's the same and no evolution. It's just population dynamics. Then they look at population dynamics, and they find you can have bistability and you can have non-equilibrium dynamics and equilibrium switching. And that's, of course, if you want to do evolutionary analysis, hell, and you want to stay away from that. So we cheated, and we only choose parameters where outside of this. So we choose parameters where we get nicely population dynamical fixed point equilibria. Yes, I didn't.
Aha. Well, but then my following question is like, so many of these models where you have ontogenetic niche shifts, what you find is that the population in equilibrium is limited either by maturation or by reproduction.
Yes.
But so the limitation by resources is never the same in the two stages, because, and that's it. To me, I always think about that. That's a kind of saddle point. If you have equal limitation in the two stages by resources, so it's either juveniles are more limited or adults are more limited.
Yes.
So, what are your populations look like when you have these traits? Are they mostly limited by juvenile resources or mostly limited by adult resources?
So I'm not sure I can answer this question very well. So this is like in type of analysis similar to Sebastian. So here we have juvenile density, adult density. We can do an isocline analysis. And then depending on the parameters that determine the shape of these isoclines. So here we have actually symmetry. Here we have a population that is adult dominated. Here is juvenile dominated. And then what Sebastian is excited about is this case, right? So we have bistability separated by a saddle point.
Yeah, but if you go back to the previous slide, so which of the two parameter settings did you use? The adult
juvenile dominated.
Ah, interesting. Good, nice.
So we are in this world here. So
you're in that world.
That is why sort of in this slide, we see that we have branching in the juvenile trait and stabilizing selection in the adult trait. So there are more juveniles, competition is more intense, driving disruptive selection in the juvenile trait, but not yet in the adult trait.
Understood. Yeah.
Thank you so much. Are there any last questions?
The number of participants is decreasing asymptotically to 0.
But their interest grows exponentially. Okay. Thanks, Klaus.
Yeah, it was so much fun to talk to you guys.
Thank you so much. Yes, so we'll be in touch about when the next seminar will be and hope to see you all there.
Okay.
So it is in next week.
Oh, it's already
next
week.
In the next week, Eric Pedersen.
Thank you. Perfect. So
1 week from now. So
fantastic.
And Klaus, please send me your presentation PDF, okay?
Okay, you want like I sent you a PDF of the PowerPoints or?
No, the PDF.